Okay, the goal of this lecture is to discuss the discrete wavelet transform. In this course, we're not going to do any actual work with the discrete wavelet transform unless you choose to do so as part of your project. And I should also comment that your author has implemented the discrete wavelet transform using very basic signal processing tools within MATLAB, but there is a wavelet toolbox within MATLAB that can much more efficiently execute a lot of the things that are shown in this chapter, which is one of the reasons that we're not going to do homework on the latter half of the chapter, but rather we'll look or refer you to look at the wavelet toolbox on MATLAB. So the continuous wavelet transform, as we saw in the previous lecture, is very redundant. In other words, you get a lot more coefficients than you need to specify the signal. There is some frequency overlap in the scale of decomposition. And so the problem with that is basically the bottom line is the wavelets are not orthogonal. They contain redundant information. So if your application calls that you recover the original signal, then you've got to have all those coefficients and quite intensive computational effort. So when you require a bilateral transform, in other words, a forward and a backward transform, then you really want as few coefficients as possible. And that's done by the discrete wavelet transform. And it's basically done in a couple of ways. First of all, when you take a discrete wavelet transform, you're going to reduce the variation in translation and scale, usually to powers of 2. And then secondly, you're going to downsample the scaled data. So in discrete wavelet transform, you have something known as a scaling function, and that facilitates how this is computed. And so the other thing is you compute the finest resolution first, and then you do coarser and coarser resolutions. And instead of starting on the original waveform, you used a smooth version of the fine resolution waveform. So there's a figure that shows up in a slide or two that will illustrate this a little more clearly. But basically, here's the equation for how we're going to do the signal, the smooth version. So let me go to the expression of the wavelet itself. So we're going to have this scaling function that contains this function phi, which incorporates the shift, and d of n, which defines the scale. So basically, as opposed to the continuous wavelet transform, where shift and scale are done within the wavelet function psi, here we have a separable shift and scale that define a discrete wavelet, and so then the actual wavelet itself is a summation of this across n. However, the way this is usually actually physically implemented is not as an actual wavelet transform, but using filter bank techniques within MATLAB. And so that's one of the reasons that we're not going to go into this in great depth in the homework, is that we haven't really had time this semester or in this course to cover filter banks. But we will have this lecture to go over basically how this is implemented. So a filter bank is just a group of filters that operate on a signal. So you have some input signal, and then you have these two filters, and you put the signal into both filters, and you get one output here and one output here. And in the case of what we're going to do, one of them is low pass and one of them is high pass. And so the two filter transfer functions have the following shape in the frequency band, so it would look relatively flat if you took the sum of all of those. So they have a low pass and high pass subband. And then, if you wish, once you have the signal decomposed into a low pass and high pass, you can do some stuff to it. And then you take the inverse filter operation and sum the components back together, and you get your new signal. And so usually this is done if, for example, you wanted to remove high frequency noise. Then you might impose this filter bank, and Then in your operations phase, maybe you would zero out the information that comes out of the high pass filter so that then when you take its inverse operation, you're effectively adding 0 to the low pass part of the filter. So you might ask yourself, why would you not just low pass filter the data? And the answer to that is often you don't know. First of all, often you have more than two. So you might have multiple stages. And secondly, you don't know necessarily what you need to do until you look at your outputs. So sometimes the decision's not made until the subband information is available. So normally you would need extra points if you're using a filter bank approach, but if you choose your filters carefully, you can basically limit your points to be the same as your original data. So filtered signal samples are reduced by 1/2 by eliminating every other point, and this is known as downsampling. And sometimes the symbol downward arrow 2 is used to indicate downsampling. After you operate on them, they're upsampled. You replace the missing points with zeros, and then you replace the zeros with the correct data. So that's the approach. You downsample really to save computational time. So here's an example of a wavelet approach using 3 filter banks. So in this case, you have a low pass and a high pass, and you take your high pass output directly. So this is what we meant by the finer analysis is done first. So this is a done deal, this high pass part. Sorry. But then you take your low pass part and you further split it into an additional low pass and high pass. And of course, each time you do this, you downsample by 2. Then, when you're ready to reassemble the signal, you take your first stage, which is your low pass and your high pass 2, and you put them back together right here. And then you take your high pass 1 and you put it back together here. And then you have your signal. If you do nothing to it, you should have your original signal back. So you can actually do this multiple times. And what that allows you to do is that allows you to look at all different levels of the filtered data and determine if there is a desired or undesired feature in one of the levels and zero out the undesired, keep the desired. So the filter bank design, if you have only 2 filters, then you have to do some things that basically in the recovery of your signal, because you are downsampling, you have to do some things for anti-aliasing. And so there are some filter bank kinds of things that you can do for anti-aliasing, and this is done in the Z domain. And since we didn't cover the Z transform in here, we're going to skip over a lot of this, just for those of you that have had DSP, so that you're aware that it is there and it is the technique that is used. So you would really like to have, so the question becomes then, as you do this decomposition, how physically is it done? What you would really like is you would really like to have subband signals that are orthogonal. And this constrains your filters quite a lot. And so there's no perfect filter, but there is a family of filters developed by Debashi, and she, I believe, developed maybe 8, and so they are known as DB1, DB2, and so on, based on how many coefficients they have. So the DB4 has the following, can be implemented using the following filter coefficients, normalized filter coefficients. And then, so this would be the low pass filter, the coefficients of the low pass filter. So here's what the filters look like. Here's the DB4, here's the DB10. You can see they have some structure, and then here are the frequency characteristics, the low pass frequency characteristics. The thing that is kind of unique about the DB filters is, I mean, if you look at this DB10, you notice it kind of looks like a heartbeat signature. So the reason they're so popular in biomedical engineering is that they tend to sort of look like biomedical signals. And remember back originally when we talked about the wavelet transform, going back to our visualization of the continuous wavelet transform, it really is almost like a convolution between the wavelet shape and the signal shape. So if you have a wavelet shape that looks like a signal shape that you're looking for, then you're more likely to be able to identify features within the signal and to eliminate noise that's not a part of your signal. So there are some things that you have to do to construct your additional filters from your low pass filter, assuming N coefficients. And then once your analysis filters have been constructed, then you can construct your synthesis filters using those equations in the Z domain. So once again, because we didn't really discuss Z transforms and digital filtering, we'll show this just for your edification so that those of you who have had a DSP course can follow that a bit. The filter banks can be constructed using the filter routine or simply by convolution. Your textbook author uses the convolution approach, and then he uses the same option to generate a non-causal output that is not time shifted. All the examples here are going to use the DAUB routine, which gives you the coefficients of the dB filter. And so in this case, I believe he gives you dB6 and dB10. So the first thing to do is to decompose and recover using 4 levels. Design a filter bank using 6-element filters. There are 2 routines that the author provides for you, analyze and synthesis. So analyze is going to take your signal, the low pass filter coefficient, and the decomposition level. It's going to build the filters and it's going to give you the decomposed signal as an output. And then synthesis will take the decomposed signal along with the levels in the low pass filter and give you the reconstructed signal as the output. So if you don't do any operation in between on the decomposed signal, then you should get the original signal back. So here's the code for that, the analyze and synthesize. So let's look at what's really going on here. So we have a signal with endpoints. And this is an example of a 3-level decomposition. So we're going to decompose low pass and high pass. And then we're going to take the low pass part and we're going to further decompose it into low pass and high pass. And then we're going to take the low pass part of that and we're going to further decompose into low pass and high pass. And so each one of these, if you'll note, as you go through the decomposition, has half the points of the previous one. So you're not really taking up a lot of extra computer memory because you're basically reutilizing the memory that you had in the first decomposition level. And because you haven't yet done away with any actual information, then you're okay. So here's the analyze routine and filter outputs and the synthesize, and I want to flip forward to look at the output. So here's a signal and here's its output, and you notice there's actually very little change. The randomness in the noise is going to change a little bit between input and output, but basically the signal looks virtually the same. A little bit of a difference at the end of the data record length and the beginning of the data record length. You notice there's a little bit more smoothing, which is most likely due to a windowing effect that's applied to the signal analysis. This is what I wanted to really look at. So here is our original signal, and it's decomposed into its high pass and low pass part. And then the high pass part of the signal is retained, and the lower pass output is decomposed into a low and high. And then that decomposition is decomposed into a low and a high. And then that decomposition is decomposed into a low and a high, and so on. And so this is a 1, 2, 3 level decomposition. You can see by the third level that this is beginning to look very smooth. And so if you wanted to denoise this, then one thing to do would be to get rid of some of these, or to zero out some of these high pass output components. So these plots show the output of the various filters. Only the low pass subband is included in the output and used in the synthesis. So we can basically take that same example and show how wavelet analysis can be used to denoise the sample by eliminating those two higher frequency subbands. Eliminate samples that are below a certain threshold value. Set those to 0. The author says the threshold value should be set to 7 times the variance of the high pass subbands. So, okay, this is a little arbitrary as well. It really depends on your application and what you're looking for. So in an actual data analysis, you might actually set your MATLAB code to loop and see what happens as you change this threshold value. So here's an example of what happens when you do that. You can see that the noise has been decreased fairly significantly. And then the comment made by the author is that as you increase the threshold, that's going to reduce the noise even further. You know, this is one way. So once again, you might ask, why not just low pass filter the data? You know, in this particular example, there's probably not a strong advantage of using the wavelets. There are other examples where it makes more sense to use a wavelet transform, particularly if there's a characteristic feature like an eye blink or a movement or something that you're wanting to eliminate from your data set that corresponds to a particular level of wavelet decomposition. Or maybe you're trying to extract from one of the wavelet coefficients itself some feature within the signal. So either one of those would be reason that you might want to play around with the threshold value and look at what happens when you eliminate certain coefficients.